You did. It was so funny.
Okay, welcome to the meeting number 8 of the class. So we are completing the part 1, and ideally there should be 6, but typically there will be no time for part 6, maybe 5. And we are completing the basics, and we'll start applying, well, getting a few more new theories and applying our knowledge to different systems, models. And today there will be a summary of basic postulates of quantum theory, which is a background for physical chemistry. Yeah, it's high resolution figure. So we'll just go in a line, and then after 6 postulates there will be a little refresher on linear algebra. So if you never have seen Microsoft Windows and PowerPoint, which I don't, then they are here. Your slides are arranged first, second in the number. You click on here and click on the place there to start the presentation. Please count. Think of the possible time for questions, and the first presenter is Amelia Anderson. Did you match the figure correctly?
Yes, that is,
okay.
That is me.
Okay, please postulate number 1.
Okay, so I have postulate number 1, and it's the foundation for all of the other postulates to build off of. You really need to understand this one in order to understand all the ones that you're going to present on. And it basically states that the state of a quantum mechanical system is completely specified by a function psi of q1, q2, all the way to qn that depends on the coordinates of the particle and on time. So the variables that the wave function generally has, it usually has 3 variables and time for every particle in the wave function, such that if there's one particle, then there's going to be 4 different variables, x, y, z, and time in Cartesian coordinates, or those ones in polar coordinates. Don't know exactly what they are, but many other sets of coordinates.
So they're not polar, they're spherical, probably.
Yeah.
Okay.
Most other sets of coordinates could be used if there's only 4 variables. And all possible information about the system can be derived from the wave function as long as you know the particle's starting position and the wave function itself. The properties of the wave function that need to be satisfied in order to use it, it needs to be single valued, so for every time there's only one measurable position. It needs to be continuous. There can't be any jumps or breaks in the function from one place to another. And it needs to be finite, such that solutions to the wave function are between negative infinity and infinity, meaning that the particle is found somewhere in space. And then once all those conditions for the wave function are satisfied, then the normalization condition is satisfied. So the integral from negative infinity to infinity of that function is equal to 1, which basically states that in all of space, the probability of finding the particle you're looking for is 100%.
Okay, let's thank Amelia. And the presentation is open for discussion. I mean, please wait. We will establish tradition to ask questions. So, and while someone is presenting, please try to think how can you please the speaker with a question? Can you please go to the previous slide?
Yes.
So your function depends on n variables, and you integrate over only one variable. Is there any discontinuity in this?
Probably.
Should it be like n integrals over each of variables?
That would make sense, yes.
Okay. More questions to Amelia? If not, let's thank her once again. And the next presenter is John Swanson. So, will you be able to close and open?
All right, so I am presenting on the second postulate of quantum mechanics. As you can see here, some may say that this is like climbing up a steep mountain trying to learn about it, but I think it's fairly simple if you get some of the basics down. So first, I'm just kind of going to give the basic definition of it, kind of walk you through it. So some of the terms that may not be as familiar can become a little easier to understand. So first, the definition is to every observable, there corresponds a Hermitian operator given by certain rules, which we will see later. So a few things. An observable is basically any measurable physical quantity. So that could be momentum, angular momentum, position is another one that's listed. I think there's a few more, but those are just kind of the style of what they might look like. An operator is basically something that brings you from one function to another. So think of f of g to g of x. And then more specifically, a Hermitian operator is kind of a more specific style of operator that has some rules applied to it. This here is a little confusing, the notation of that, because that gets into linear algebra. So I'm going to give an alternate definition a little later on that will kind of clarify what exactly that means. So the details of it, this postulate has three little subpoints that kind of help define it. So first, the first two basically show some of the more simple types of Hermitian operators. So for x, there is a corresponding operator for a Cartesian position. And again, I will give this example what exactly that looks like in a few slides. Likewise, for p of x, the component of linear momentum corresponding to x, there is this function, which is the partial derivative of Planck's constant over imaginary I. And that is the Hermitian operator for position function. And that applies for x, y, z. You just change the variable from y to z from x. So this third one I think is the most important and the one that you should focus on kind of knowing. And basically it says, I'm just going to read it because it explains it pretty well. So to obtain the operator corresponding to any other observable in terms of x, y, z, px, py, pz, and then replace each of these quantities by its corresponding operator according to the rules 1 and 2. So basically if you have a function that has some undetermined things, if you can replace it with x, y, and z, p sub x, p sub y, p sub z, you can easily get it to something that's more understandable rather than a mess of other terms. So this is the integral definition. I made this PowerPoint on a different system, and so all of my functions got mixed up, but I'll try to explain what this means nonetheless. So basically, it's a Hermitian operator if A is equal to A star. And that can be defined by this integral. So you have this star A, and then another, I'm not sure what that Greek letter is, but, and then that will be equal to these two switched with the star times this one. So this is supposed to say something in English. I don't know what it's supposed to say.
This is also true for.
Thank you. Wow. So this is also true when these have subpoints. So 1 and 2, equivalent, the 1 and 2 stay there. So that's basically showing that these are separate quantities. And so that's should be a little more clear with a good example that has actual English. So this is for a equal to x. So when you have this star x, this 2, this is equivalent to if you have this, you can add the star because basically for x, x equals to x star if it's a Hermitian. So if you add the star here, these two are equal, right? And then you can kind of factor out this star, and you're left with that at the end. And because it goes from that to that, by definition, it is a Hermitian operator. That's all I have. Does anyone have any questions?
Okay, good time, John. Any questions? Or it was crystal clear? Okay, it's nice talk. No questions. Thanks once again. So, Yunke Hong,
Yep.
you will present postulate number 3.
Yep.
Will we be able to switch, close one, open another?
Yep. Hello, my name is Yunke Hong, and today I will introduce an interesting postulate which was built in the class. The postulate is the only possible result which can be obtained when a measurement is made of an observable whose operator is A in an eigenvalue of A. It sounds like a little bit confusing. It doesn't look like straightforward and seems like very hard to understand. But if you look at this sentence carefully, we can find 4 important keywords, which are measurement, observable, operator, and eigenvalue. First keyword is measurement. Measurement is a collection. Measurement is a collection. Is a collection of a quantitative or numeric data that describes a property of an object, and observable means a physical quantity and that can be measured. An operator is an object that is capable of manipulating a value or operator. And eigenvalue means each of the set of values of a parameter for which a differential equation has a non-zero solution under given conditions. So I found out that this postulate is highly related to one equation, which is an eigenvalue equation. This is how eigenvalue equation looks like. It looks complicated, but we see this equation and analyze what is what. It became straightforward. First letter appears is A. This is an operator for the equation. And the second is psi. This is an eigenfunction of operator A. An eigenfunction means a set of independent functions which are the solutions to given differential equation. The last one is another psi, which is again eigenfunction of initial state of operator A. It should be a real number because of the observable property of an object. The last one is another psi, which is again eigenfunction of initial state of operator A. So with understanding the equation here, the postulate can be rewritten as more simple and straightforward sentence, which is according to eigenvalue equation, any measurement of an observable property A will only yield eigenvalues for the operator of A. It looks way more straightforward and easy to understand because this is a direct interpretation of this eigenvalue equation. Thank you.
Oh, that's it. Okay. Questions? I have several.
Yeah.
So, in your equation?
Yeah.
Yes. So, there are 2 symbols psi.
Yeah.
And one of them has index I and another does not. Do you miss to place it, or there is some deep meaning in that?
So on the right-hand side, which initial I means initial state, which is the first, which is the initial state of the equation, and this left-hand side of psi means afterwards thing.
Okay. Interesting.
So
Because
after calculating
Mhm.
the operator, it becomes the right-hand side of psi, which is not anymore initial state, which is a present or final state.
it is a deep meaning, but typically when we see in class, we should always put I after psi for practical problem solving. So it is a common thing. Question number 2. Can you give examples of measurements and observables that where these properties are manifested?
Measurements is is it written like as a collection of quantitative and numeric data, which can be an energy or position or
So yes, it's enough. But example, how the apparatus to measure energy or position would look like. And it is a tough question. If anyone wants to help, it will be appreciated. Huh? So
can you repeat the question, please?
example of the instrument that measure, give specific example of instrument experiment that gives you observable. Yeah, spectrophotometer. And if you take a spectrum of an atom, how does your spectrum look like?
Wait for possibility.
Yes, it kind of depends on
You can show by hands what is your vision of spectrum. Yes, there are peaks. And peaks, if it is atomic, then they're very narrow, right? So when these peaks appear? At certain energies or certain energy differences. So in some sense, measurement of spectrum reflects the measurement of energy. And you get only eigenvalues of energy, only these discrete values. Okay? So it's not straightforward translation of what you presented, but there is a connection. Okay, yeah. More questions? If no, let's thanks you once again. And next presenter is Alyssa Roberts. She is presenter number 4, and she is presenting postulate number 4.
All right, so fourth postulate of quantum mechanics. So the postulate reads, let alpha be an observable whose operator A has a set of eigenfunctions phi j with corresponding eigenvalues of aj if a large number of measurements of A are made on a system psi, then the expectation value for A for the system psi, i.e. the arithmetic mean of the eigenvalues obtained is given by the function, where d, well, I guess, I don't know if it's supposed to be r or if it's supposed to be tau, but that is an element of volume where the integral is taken over all space. So that's just a lot of words. So the A in this equation, or I have it as capital A rather than alpha, but I believe that they're the same thing, is the physical observable that is produced by the equation. So as we talked about before, it's either position or energy or whatever you're looking for. It's the mean of all of the eigenvalues. So this function is normalized. I didn't include it in my PowerPoint, but it is. So it's divided by a normalized function to give it the mean of the properties. And then the d, tau, or r, or whatever you want to use, is indicated for the integral over all of space. So the integral itself is from negative to positive infinity. So it's just including everything. And then the A with the hat over it is the operator, altering wave function, which could be the position operator, or we have that whole sheet of operators that we could use. So whatever you want to pick for that day. And then I have a lovely graph.
Jason Penny has that too long.
And this is the last thing we didn't talk about is what the size of the size is.
That like
Oh,
oh, I do.
I'm so sorry.
Okay.
to do that. There's a screenshot of me, and I was excited because it had the, anyways, doesn't matter. So this is the board interpretation. So as we know from class, wave functions have imaginary components. So if you want a real observable, you can't have an imaginary component to your real observable. So the conjugate is reused to remove the, like the conjugate, the psi star, is used to remove the imaginary part of the wave function. And so an example that I'm sure we've all seen before is when you take the positive of the conjugate and then you end up with an actual observable value for this. And yeah, and so basically all those parts come together and give you an actual answer that you would use. That's it.
Okay, let's thank Elisa. Any questions to the speaker? Oh, please.
For the d tau, the delta tau, is that essentially, depending on your operator, your derivative?
I'm assuming so. That's probably why they don't count it as dr, so that you can replace it with like dx, or you can do the dx dy. Yeah, exactly.
So I have a question. Do you see any contradiction between the postulate that you presented and the postulate that Jung presented? So he told that you can measure only discrete, as a result of measurements, there is coming only certain values, discrete values, which are eigenvalues. You're telling that one can get some intermediate values in between.
Well, it's the mean.
Yes, yes. So you can get mean value. Can you? Is there a contradiction or there is no? How do you see it?
I don't know.
Is that the difference of wave and non-wave?
No. And it is fine. It is a challenging question, so we can think.
Well, doesn't the wave function have multiple answers? Is that what you're trying to get at? So there's like not one specific eigenvalue for it.
If you show your first slide once again.
Because didn't his say kind of like the only like observe or something? What was it again? The only result from an observable is the eigenvalue of it. And then hers is kind of saying, well, there's more, right?
Yes, but she never told that out of one measurement there will be different. She told like if there is a collection of independent observations. So if we can have one atom and one observation, like one quantum comes, then everything is same as in Newton. But if you have ensemble of billion of atoms and measurement of all of them and adding together, then the result can be somewhere in between. So the keyword here is the number of measurements. So it's several measurements. Okay. More questions? If not, let's thank Alisa once again. And we are doing really good with timing. So, Morgan, you present on the postulate number 5, and it seems to be dealing with measurements as well, right?
Yes.
Before we start with the question, wouldn't both of their presentations be correct in that the wave function has to be continuous? So even if you only measure the speech values, there has to be
There is a thing that is out of box of the quantum theory. Quantum theory, in narrow sense, doesn't consider ensembles, and measurements cannot be done without ensembles. So there are no problems with wave function. There is a problem with real worlds that have as many atoms or measurements are repeated again.
Okay, so my presentation is on the 5th postulate, and I realized that I actually didn't put the postulate in there anywhere. So my postulate reads, if the result of a measurement of alpha is alpha r, corresponding to the eigenfunction phi r, then the state function immediately after the measurement is phi r. So basically, it's saying like if you try to measure something, while you're doing it, it's going to change the system. So, which seems kind of difficult that you're trying to measure something that kind of moves away as you try to measure it. And so the way that this is done, basically, as this is moving, what they do is they find a sort of trace of how this, I guess in this situation, I kind of thought of it as a particle or like an electron. If you try to measure its location, the trace of where it went, you can then use to kind of replace it mathematically. And so then you can do more measurements on it without kind of adding this difference to each measurement. And so this act of replacing it allows you to do other measurements, so then your answers don't continue to get off. And one example, kind of an explanation I found of this was called Schrödinger's cat. And it didn't really make a whole lot of sense to me, but it's saying that, like, you know, if a mechanism is arranged to kill a cat in a quantum event such as the decay of a radioactive atom occurs, then the fate of the large-scale object, the cat, is entangled with the fate of the quantum object, the atom. I guess this one didn't really make sense to me, but another analogy I kind of thought of is sort of like you try to grab like a piece of cotton out of the air, and it just like keeps moving away, and like you can't get it. So that's kind of the analogy I came up with. But yeah, that's it.
Okay, questions?
So for the Schrödinger's cat analogy, that's a question on this thing that you don't really understand so much, but is it kind of saying, like, because Schrödinger's cat's like the cats are both dead and alive at the same time? So it's kind of like saying the electron or whatever you're measuring is like both in the spot that you first found it, but also probably not.
Yeah, it's kind of like what he was saying, where like the wave function isn't wrong. It's like the real world that doesn't match up with the wave function type of thing. I think it's sort of like that. But I think what they're trying to get at is that, like, this, you know, thing that's sort of separate, same as the measurement is sort of separate to the particle, it still like affects it and has some influence on it. I think that's kind of what that's trying to get at. But I was trying to figure out that analogy didn't really make a whole lot of sense to me, personally.
I have a different question. I don't know if you know, but do you know if there's a difference between an eigenfunction and a state function?
I don't. Is that just the original?
Each eigenfunction is state function, but not each state function is eigenfunction.
That helps.
Any wave function is a state function, but not any wave function is eigenfunction of a certain operator or Hamiltonian.
All rectangles are square. No, all squares are rectangles, not all rectangles.
Yes. All trees, all oaks are trees, but not oaks are trees. I have a comment. If there are no more questions about John's question. Remember last thing we did in class about differential equations and constructing partial solution out of general solution. So one can add at least 2 or maybe more general solutions into partial, and it still will be a good solution. So one of these general solutions can correspond to like ground state quantum particle, another can be excited particle, and their superposition is permitted by algebra, by math of quantum theory. But if excited state launches some measurement and kills the cat, and ground state does not, then it creates a paradox. So this quantum object can coexist in 2 states, but through our common sense, cats do not coexist in 2 states. And this thought experiment creates a paradox. I don't know if I made it clear, but at least we have been introduced to this paradox. More questions to Morgan? If no, then thank you once again. Kristen? Yours? And it looks like this presentation you have largest number of equations.
Yeah.
Oh, yes, yes. Is that okay? So I have a couple of notes.
That's okay. If your notes are not secret for the rest of us, then.
So I'm presenting on postulate 6, which is the time variation of the state function, which more commonly known to us is the Schrödinger equation itself. So the background on that is that the Schrödinger equation was developed by Erwin Schrödinger in the 1920s. The nature of psi, or the wave function that we've been using, was later defined by Max Born in 1926 as the probability amplitude whose modulus squared is equal to the probability density. And those were a lot of terms that I didn't know. So the probability amplitude is a complex number which is used in describing the behavior of systems. And that still didn't help me understand. So then the probability amplitudes provide a relationship between wave functions of a system and the results of observations of that system. And that leads into the probability density, which we did touch on. And essentially we use this to predict the likelihood of finding an electron in a particular space at a particular time. Which is what the Schrödinger equation works to do. It's a linear partial differential equation that describes our wave function or state function, which defines the state of the system at each spatial position in time. So time variation of the state function, we've seen it before, is our Schrödinger equation where we have derivative of psi with respect to time, which is equal to our imaginary number over Planck's constant, which is that h bar, times the Hamiltonian and psi. The Hamiltonian is the sum of our kinetic and potential energy, which means this varies for every single system. Because although kinetic energy is a standard equation that is set for all systems, the potential energy will be dependent on our system as that equation varies. Oftentimes, it will relate though to the Laplace operator that we see in the kinetic energy equation, and that is more commonly known as the gradient, which you've seen in multivariate calculus, which is just the sum of your partial derivatives of your value, whatever that might be. So what are some of the applications of the Schrödinger equation? They have 3 different ways to predict that feature of our wave function, and we actually got to do all 3 of these in class at this point. So the first one is to use an evolution operator, and that way we multiply that evolution operator by our previous or past wave function in order to predict the future wave function. In the second option, we use finite difference increments, and that's breaking down our time difference into very finite pieces and summing those together to again predict the future of our wave function. And that last version of the equation is to use our eigenvalues or eigenstates matching, in which case we solve for eigenfunctions and eigenvalues, and as I said, they then predict our future wave function.
Okay, well, thank Kristen. Any questions? I don't have a smart question, I have a silly one. In Schrödinger equation, you have imaginary unit in denominator.
Okay.
Why it is in denominator rather than numerator, and can you move it up?
You can exist negative imaginary number, and so you can raise it to the power of -1.
Okay. And I do not have smarter questions. More questions 1, more questions 2, more questions 3. Okay, thank you once again. And last but not least, Stephen Westra will refresh some of our members about linear algebra.
So, what allows us to, so are we, as you said, presenting on a refresher for very basic invariants in algebraic functions, in particular dot product and its use in matrix multiplication. So a dot product is a simple algebraic mathematical function involving 2 scalars, that is, 2 objects defined by coordinates that have both a direction and a magnitude when on a Cartesian plane. And an example of a dot product would be a multiplication of the coordinates for 2 line segments as one of the most common uses. So if we have 2 vectors, vector x and vector y, with coordinates x1 and x2 and y1 and y2, we can take the dot product xy, which is equal to the sum of all numbers along the number line of each line. And we can multiply it out as x1 times y1 plus x2 times y2. And an important fact of this is that a dot product of this nature, when graphed on an ordinary xy Cartesian plane, is equal to the magnitude of each vector multiplied by the cosine function of the angle between them, as I demonstrate with the next slide. So you have vector x and vector y, which we assign values 0, 1, and 1, 0. So if we solve our dot product between them, we get 0 times 1 plus 1 times 0, which is equal to 0, which is equal to the cosine of pi over 2, which is equal to 90 degrees, which is the angle we would expect for two lines with the coordinates 0, 1, and 1, 0. So the importance is that they have many uses. Most importantly, as we've seen, they are used quite widely in other quantum equations and postulates, as we've seen in the previous presentations. And they also form the proof behind many of the trigonomic relationships that we would learn about there, as I demonstrated with the cosine is adjacent over the hypotenuse. That's possible because we can say the dot product is equal to the magnitude times the angle. It's also used in matrix multiplication. So there's matrix multiplication. So a dot product of a single vector multiplied by a table of numbers, or a matrix, is what is matrix multiplication by a vector. The important fact is that in order for this to be true, it requires that the number of columns in the matrix here is equal to the number of rows in the vector. And so we take x1, x2, x3 in matrix y1, y2, y3, z1, z2, z3, and we do dot products for all of those combinations in the same way that we did for the two vectors, and we get a table or another matrix of the dot product values for all of those numbers. So the matrix 2, 4, 6, 8, 10, 12, multiplied by vector 14, 16, 18, gives us 28, 96, 180, 56, 112, and 16. This can be further extrapolated into the matrix multiplication involving two matrices, where you have a series of dot products for two tables of matrices of numbers. And I've just realized that this is actually not calculated correctly. I don't know why that is. I thought I checked it. But if we take the matrix for 1, 3, 5, 7 and 2, 4, 6, 8, we can take dot products of those numbers and we get, it says 14, 30, 38, 86. That I can do in my head is wrong. Very sorry about that. That's all I have. Thank you. Any questions?
Okay, good then. Steven? Yes, we will have some questions.
Oh.
Any? So, in your slide number 5, you mentioned importance of dot product for trigonometry, but if you scroll back what we've heard about postulates of quantum mechanics, to which of presentations and to which of postulates the dot product would be related at most? Any relations?
Oh, right. So I believe that in postulate 1, it would be involving the dot product of the variables of the Cartesian coordinates for the wave function. Is that correct?
Would you agree that it would relate to finding normalization, the normalization condition?
Yes, I do agree.
So, how many independent projections will be if you have normalization of wave function that depends on variable x? It's a tricky question, or not straightforward. Yes. Examples that Steven was showing were demonstrated for space of dimension equal to. Suppose that you have wave function that depends on only on one variable, and then we practice dot product for multiplying one wave function onto another wave function. What will be dimension of this space?
1.
It's you were falling into this trap.
Because it's two one-dimensional things.
Yes. Yes.
So then would you get?
0.
No. No. Huh?
Does he get two-dimensional?
No.
Or 3?
No.
That's
The fourth dimension.
4.
No.
1.
No.
0.
No.
You just keep going.
We've listed all the dimensions.
Cannot be defined.
8 rotated by 90 degrees. Symbol 8.
Infinity.
Yes.
Why is that?
Huh?
Why is that?
Can I draw something? And probably let's thank Stephen once again. And, yeah, and I will just complete because it's our discussion with him brought an interesting question that we will appreciate during the class. Okay, so a little correction. It's if you're using this notation, then you do not need the sum. If you're using sum, then you do not need to explicitly mention, like I equals from 1 to n to I equals 2 of x I y I will be x1 y1 plus x2 y2, right? So either summation or explicit. Now,
I wanted to show it implicitly.
but I would put one more equality sign and show either one. Now, the wave function in presentation 1, suppose that you have only one dimension. Psi of x is equal numerically psi of x1, comma, psi of x equal to, where x, we can split our space onto values x1, x2, x3, like grid points. And then it is a vector. So we are originally here we were listing only two values, but if we are representing wave function numerically, psi of x3, comma, and then psi of x, whatever, n very big, infinity, right? And the psi star will be same things, but psi star of x1, psi star of x2, and so forth. And then the dot product will be summation, processing the same stuff. So summation of I from 1 to n, psi of x I star times psi of x I, no star. And if you want to agree with definition, you can put a little dx or delta x, which is the size of this stuff. Okay. But amount of terms in this summation is infinite.
An infinite column matrix space.
Yes. Good. Okay, well, let me thank all of you for really nice presentations. You have a little pathetic homework that is rather easy to complete, right? No one found it complicated. And On Wednesday, we'll start a session in the same building, 132, with the computers. Okay, thanks much for effort and yes.
Do we have lab this week?
Yes, yeah. It's time. Yeah.
October 16th is the Wednesday.
Okay, that's
But I'll send you an email. So, you know. Thank you.
I was trying homework and I found myself a little confusing about question number 3, the last one.
Can you scratch what you can do and send me, and I'll because
Keep taking that with you.
Yeah, just take it.
generate a specific question
I'll
for me.
grab a
What's that?
Please generate a specific question. Show how you try to do it, and then I'll show what was wrong.
I need like at
Okay,
least
thank you.
6.
Yeah, I was going to say, in a lot.
Had a few for sure.
Definitely
Also,
don't
thank
think
you for the
I'm
food.
Oh, my pleasure.
Yes, thank you.
Do not flip them. Take more.
I'm good. John, you can have both. Okay, you can have both of them.
I think I give them away to people, but I don't need them.